Hey guys, and welcome back for another ANSYS tutorial. Today I will demonstrate how to use the latest modeling technology to simulate a reinforced concrete T-joint using ANSYS Workbench version 2020 R2. The simulation results will be compared to that of actual experimental results performed by Chariolis in 2008. More details on this paper can be found in the description below. This tutorial will go over importing the geometry, setting boundary conditions where we will fix the column in place and apply a displacement of 80 millimeters downwards at the end of the beam. And finally, we will go over viewing the results, which includes the homogenized tension and compression damage by using APDL commands. We will also be using the CPT215 Elements and the reinforcement type option within mechanical to model the rebar. This is an improvement compared to my previous video, which uses solid 65 elements and the REINF commands. So let's get right to it. Start by double-clicking on the Workbench 2020 R2 shortcut, also titled Run WB2.exe. Once inside Workbench, let's go ahead and click on the units and make sure that the units are set to metric kilogram millimeters. Next, let's go ahead and drop a static structural from the analysis system into the project schematic. You can rename this to whatever you want, however, I'm going to leave this as static structural for now. Let's double-click on engineering data to set up our materials. Let's go and click on engineering data sources, and let's scroll down to general nonlinear. In general nonlinear, let's go into the outline and let's choose structural steel nonlinear and click on the plus button to add it to our engineering data. Next, let's go back up here and click on general materials and let's choose concrete over here. And let's click on the plus sign and add it to our engineering data. Next, let's click out of engineering data sources and let's delete the regular structural steel by right-clicking on it and clicking on delete. You should now have only two materials in your library, which is concrete and structural steel nonlinear. So let's go ahead and change these structural steel properties. We'll change the units for the Young modulus to megapascals, the yield strength to megapascals, and the tangent modulus to megapascals. And let's change the Young modulus to 1.9 e to the 5. And let's change the yield strength from 250 to 470 and the tangent modulus to 1000. Now if you click on the bilinear isotropic hardening, you will see here the stress-strain curve for the steel. This steel will be used for our reinforcement bar for the concrete structure. Now we will not be changing any of the concrete data here because this will be overwritten by APDL commands that I will show you later in the video. Next, let's close out of engineering data. Let's right-click on geometry and let's import a geometry. Click on Browse and import the Dr. Dalio joint geometry.scdoc. Once it's imported, let's double-click on the model to open up mechanical. Now note that this geometry is only half of the actual model. It is cut along the YX plane as you can see over here, and we use the symmetry in order to cut down on solving time. Next, let's go ahead and assign materials to the geometry. Let's click on the plus button over here under geometry and click on the plus under beams, and let's hold the control key and select all the beams over here, beam number 8, and let's change the assignment to structural steel nonlinear. Next, let's change the model type from beam to reinforcement. Note that this feature is a new feature in ANSYS Workbench 2020. Once the 8mm rebar beams are done, let's go ahead and click on the body, which is the concrete, and let's assign the material of concrete, which will again be overwritten by APDL commands. Next, we need to insert a command file for this geometry by right-clicking Insert and then clicking on Commands. And then we need to assign an arbitrary variable with a material ID, so that way the material ID for the concrete is not 0. Next, let's go ahead and select, using the Shift key, the rest of the beams, and then change the assignment, once again, to structural steel nonlinear, and change the model type from beam to reinforcement. Now if we go under materials, we will see that we have our structural steel nonlinear and the concrete, and we'll see that the geometry imported automatically the cross sections that I created. So these are the 8mm diameter rebars, 14, 10, and 12 respectively. Now in order to see the rebars, you can click on Show Wireframe, and then as you can see here, these are where the 12mm diameter rebars are. The 10, there's only one. The 14, there's two. And the 8 are all the other ones. Next, let's get out of wireframe and click back on shaded exterior edges. And now let's go ahead and set up the mesh. So let's click on mesh and let's change the element order from program controlled to linear. Now we will change the element size to 25 millimeters. Next, let's right click on mesh, insert method. Let's click on the no selection and then using the body filter tool, select the concrete body, click on apply, and let's change the method from automatic to multi-zone and ensure that the map mesh type is hexa. Next, we'll right click on mesh, click on insert, and then click on sizing. Now using the edge filter tool, by clicking on here, and we'll change the select mode to box select, we will select all the edges in the model by dragging a square over the model, and then click on apply. You should see 199 edges. Next, let's change the element size to 25 millimeters. Now we're ready to right click on mesh and click on generate mesh. Now we must check the element quality. Let's click on quality under the mesh and click on mesh metric and change it from none to element quality. You should now see that the only element in this table is hex 8 and all of them should be under 1.00. This means we have perfect cubic mesh. Now that the mesh is done, let's go and click on analysis setting. Let's change the end step time to 2 seconds. Let's change the large deflection from off to on. And now let's go ahead and add our boundary conditions. So let's right click on static structural, insert, and then let's insert a force. Now using the edge filter tool, let's take off the show mesh. Let's also change the mode from box select to single select. And now let's choose this top edge over here, click apply, and let's change the define by from vector to components. And now in the table over here on the right, let's click on the 2 and enter a 1. So that way we break down the force along 2 time steps. So 0 to 1 and then 1 to 2. And in the Y column, let's enter negative 9480 newtons. So what we're doing here is we're breaking down the compression force at the top in order to separate it from the time step for the displacement that we will apply at the bottom over here. So now let's right click and let's click on insert and then displacement. Now for the geometry selection, let's select these 4 edges over here. This one, and using the control key, select this one, and then finally this one over here, and then click on apply. You should now see 4 edges are selected. Next, we will restrict the displacement in the X direction for this by clicking on the X component, hitting 0, and then enter. This now restricts the movement of these edges along the X direction. Next, we will go and click on static structural, insert, displacement, and now let's click on the bottom edge over here, click on apply, and let's restrict the movement in the Y direction by clicking on the Y component, entering 0, and hitting enter. This will be our bottom support for the column. Next, we're going to insert the displacement at the end of the joint on the right over here. Let's right click on static structural, insert, displacement, and let's click on this edge over here, and using the control key, select this edge over here, and then click apply. Now here, let's click on the Y component and click negative 80. This will pop up the tabular data on the right. Let's change the time here from 2 to 1, which will add another column over here. And now what we want to do is change this time step from 1 second to 0, and at time 2, negative 80. So what's happening here is the force is applied from 0 to 1 second. So as you can see here, 0 to 1, we're applying a force at the top here to compress the column, and then we're maintaining that force from 1 to 2 seconds. And then under the displacement, we're not applying any displacement at the edge here, but we're applying it from step 1 to step 2. Now note that the time here in seconds is really equivalent to just steps, since this is a static analysis, and time doesn't have a meaning in this analysis. Next, we need to insert the symmetry for this model. So let's right click on model at the top, insert, and then click on symmetry. Right click on symmetry, click on insert, and click on symmetric region. Now let's click on the face filter tool and let's hold the control key and click these 3 faces over here and then click on apply. Next, we will change the symmetry normal from the x-axis to the z-axis, and that creates our symmetry normal. Now we need to enter the commands to use the CPT215 Elements for concrete. Let's right click on static structural, insert, and then click on commands. Now in this window, copy and paste the commands for /prep7. These commands will be given in the description below. So this model uses a 3-surface Druker-Prager model, which is equipped with a tension and compression cap to simulate the complex triaxial behavior of concrete. So here is a table for the material parameters for concrete that's used in this model. Now, as you can see, there's quite a bit of parameters. Some of the basic ones, such as Young's modulus, Poisson's ratio, and the compressive strength, are fairly standard, and they're normally determined experimentally, or you can find them online or from different suppliers. Now, the rest of the parameters could be harder to find, such as the compression cap location and the damage parameters. And I've provided a few formulas here to help you out in case you don't have the exact values. So these are approximate guidelines that you can use. Now, coming back to our command, we can see that we're defining the CTP element over here. We are determining here the elastic modulus, the Poisson ratio. Here we're saying to use the Druker-Prager model, and then here are the location for the table data for the parameters such as FUC, FBC, FUT, etc. And then the same thing here, this is a continuation of the parameters that you need to input. And then finally, as well as the non-local parameters over here, which are the parameters C and M. And that's essentially it. And then next, all we're doing is we're selecting the already created solid 185 elements, and we're switching it to the CPT215. So this is the command file that essentially converts the already generated standard solid elements, and it's converting it to the CPT215 elements. All right, now that's done. Let's scroll down to Solution, right-click on Solution, and let's start inserting a deformation and click on Total Deformation. And now let's also click on Solution. I forgot to click on Beam Section Results and change that from No to Yes. And now let's select all the rebar and apply a named selection for this. So using the Body Filter tool, click on this body, right-click, and then hide the body. And now using the Select mode to Box Select, let's select all the rebar. And let's right-click, and then let's click on Name Selection, and let's type in Rebar. Then click on OK. And now let's right-click, and then click on Show All Bodies again, and let's change the Select mode back to Single Select. Now we can see here that we have a named selection that was created, and it's called Rebar. Now once that's done, let's right-click on Solution again, Insert, and let's add Strain component, and let's add equivalent plastic strain. And instead of using geometry selection, let's use the name selection, and let's click on Rebar. Now let's right-click on Solution, Insert, and then let's click on Stress, equivalent von Mises stress, and then let's click on Geometry, Name Selection, and then let's choose Rebar once again. And now let's right-click on Solution, Insert, Strain, and then let's click on Equivalent Plastic Strain, and let's select the concrete body, and then click on Apply. And now we can rename this, so let's rename Deformation Total. We'll type in All Bodies. For this one, it's the rebar, so let's right-click and rename Equivalent Plastic Strain Rebar. And then let's click on Equivalent Stress, right-click, rename, and then type in Rebar. And then for this one over here, let's right-click, rename, and then let's type in Concrete. Now finally, we need to export the directional deformation as well as the force reaction in order to create the chart that was used in the original paper from 2008. So in order to do this, let's right-click on Solution, Insert, Deformation, Directional Deformation. Using the Edge Filter tool, let's click on this bottom edge, and then let's click on Apply, and let's change the orientation from X to Y. Next, let's click on Solution, Insert, Probe, and then let's probe the force reaction. And then let's use displacement 3, which was the displacement that was used at the end of the beam over here. And finally, we're going to insert some command files in order to output the homogenized total damage, the homogenized tension damage, and the homogenized compression damage, as well as the split weight factor. So let's click on Solution, Insert, Commands, and copy the command files that are given in the description below. The commands should start with /show, PNG. Now here are the total damage, compression damage, tension damage, and the split weight factor that will be plotted under these command files. Now we're almost ready to solve. Now before doing so, let's just double click the solve properties here. Just make sure that it's clicked on distributed, and you can select the number of cores that you would like to input for your solver. Once that's done, let's go ahead and click on the solve button over here. Meanwhile, it's solving, we can click on the solution information and change it from solver output to force convergence in order to follow the convergence of the solution. Now, just to give you an idea, this took about 15 minutes to solve on my computer. Now, once it's finished solving, as you can see here, I've had about 468 iterations in order to solve. Now, to view the results, we can go ahead and click on the total deformation for all bodies. And as we can see here, we have a total deformation of 89. That's because the applied deformation is slightly before the end of the beam. So that means the end of the beam deforms slightly more at this edge over here. We can go ahead and play an animation for this by clicking on the plus button here. And we can see the animation for how it deforms. We can also change under the results tab here we can change the scale from auto scale to, let's say, something more exaggerated, such as a 5x. So as you can see here, this is a much more greatly exaggerated deformation animation. And we can go ahead and put that back to auto scale. And next we can view the equivalent plastic strain for the reinforcement bar. So as you can see here, the rebar has plastically deformed in this region over here. You can see approximately when that happens is around a displacement of half of the total, which is 80 millimeters. So 1.5 is at about 40 millimeters of displacement. The rebar begins to plastically deform. So that's what this chart shows. Once again, we can play the animation and then we can see it plastically deform. Next, we can go and check out the equivalent stress. So as you can see here, as we'd expect, since it plastically deformed, the equivalent von Mises stress should have hit its maximum, and it does. And so that's what you see over here. We can go ahead and play that animation as well. Next, we can click on the equivalent plastic strain for the concrete. And then we have the directional deformation, which will be used for our chart, and the force reaction as well. And let's go ahead and click on the plus button here for the APDL commands. Now, just a reminder, the first chart is the homogenized total damage, or TOTA. So we can click on the output over here, and we can see here it's MPDP TOTA average. So this is the chart for the total damage. And then the second one is the compression damage. So here we have the chart for the compression damage. The third one is tension damage. So that's the chart for the tension damage. And then finally, we have the split weight factor as well. Now, in order to create the chart, in order to compare it to the results from the paper, let's go ahead and click on the control key, click on the force reaction, and then click on directional deformation. And then under result tab, let's click on chart. Now let's change the x-axis from time to directional deformation max. Let's change the input quantities time from display to omit. And let's also omit a few others over here. So let's omit the directional deformation as the output. Let's remove the x force, and let's remove the force in the z direction as well as the total. Let's omit that. So now we're only left with a displacement versus vertical reaction force in the y direction. Now what you can do is you can go ahead and select these columns, right click and either export the results or just copy cells and then paste them into Excel. Now I've already done this, so let's go ahead and open up the Excel sheet. So here's my Excel sheet. Now as you may notice, the curve is different from the one we saw in the ANSYS Workbench video, and that's because I just tweaked it in order to change the sign. So essentially the displacement was showing up as negative because it was going in the negative y direction. So I just applied a formula of -1 to flip that sign into the positive direction. So now it goes from 0 to plus 80. And for the force, it was also displaying in the negative values. So what I did was I multiplied by negative, and also it's in newtons, and here I would like to display it in kilonewtons in order to compare it. So I divided by 1,000, multiplied by negative, and in this case -2, because we have to remember that this model is a symmetry, and so that the resultant force of the model is actually only half of what the full model sees. So that's why I also multiplied by 2 in order to compare it properly with the experimental results. So as you can see here, the simulation that we've done together is shown in red over here, and The simulation that was done by the paper from ANSYS is in gray over here, and the experimental data, which is, we could call it the true data, is shown in blue. And as you can see, I've actually done better than the ANSYS Inc. data, and I'm actually matching almost perfectly here in this region with the experimental data and tapering off as well. So as you can see here, we've come almost extremely close with the experimental data. Now let's head back into ANSYS Mechanical. So let's minimize out of the Excel chart. And a few other things before I finish off the tutorial. Keep in mind that all of these results are shown at time equals last. So that's at the last time step. If you would like to see, let's say, the rebar at 40 millimeters of displacement, approximately you can enter a display time of 1.5 and then retrieve this result, and then you can see the result at 1.5 or at 40 millimeters of displacement instead of the last time step, which is at 2 seconds. Now we can also show the maximum and minimum locations by clicking on the maximum and minimum under the results display here. So here we can see once again the maximum is shown here. And then we can also go back to total deformation. And since this is a symmetry, we can actually show the full body by using a beta feature. So let's minimize out of mechanical. Let's go into tools and then let's click on options, click on appearance, and then scrolling down to beta options and checking that box over here. Then let's click on OK. Next, let's go back into mechanical, and once in mechanical, now we can go all the way to our symmetry region and then click on symmetry, and now you can see here we have something called graphical expansion. We can change the number of times to repeat the geometry to 2, and we can change the method to half, and we want the symmetry of the repeat to be at 100 millimeters from the global coordinate system. So we can see here that it starts at this corner here, and we want it to repeat at this surface, which is 100 millimeters away. So let's go back here and enter a delta Z of 100 and click enter. And then next, if we click on the total deformation, we can see the full result. So now we're actually looking at the full geometry because all it's doing is just mirroring the geometry here. So now if we play that animation, we get the full result over here. So that concludes my tutorial. I hope you enjoyed it and learned something new. If you did, please hit that like button and don't forget to subscribe to my channel for more updates. See you next time.